Welcome to After Hours Engineering, Episode 9. We covered quite a bit of material in the previous episodes, of which the most important was the fetch, decode, and execute states. This put us in a good position to start adding and finishing the rest of the ISA by adding more instructions to the decode and execute states. This includes the R, the I, the S, the U, the B, and the J instructions. So how about we start with the RType instructions? Let's go. We need to start with the data flow diagram because that tells us precisely what we need to do. And here we are looking at the diagram. Because we're working on the RType instruction, we need to identify what in the instruction the control matrix needs to control. So to clarify the picture a little bit, let's turn off some of the other components that we're not going to need. And you can see that now we're just looking at this portion of the circuit right here. So we know for the RType instruction we have two operands that need to go to the ALU, A and B. And the output or the results of that needs to do a write back into one of the destination registers specified by this portion of the instruction register. So what signals does the control matrix up here need to emit and control in order to make that all happen? Well, we need to first of all set the write. We'll eventually need to set this write signal. We need to control where the source is coming from with this signal right here. We also need to select both the RSA and the RSB via these two signals right here. And we need to select the operation that we're going to perform. Now that we know what control signals we need to manipulate, we're ready to look at the state machine to find out where the RType instruction resides. Recall that in this section right here, we had the reset sequence going on right here. Then we had the fetch and then the decode. Down below is all the execution sections that we need to consider. And for that, we'll bring up the RType instruction. That's the one we're looking at. And here it sits, fetch, decode, and then the execute section. So I'll zoom into that, and we'll take a look at it. For the RType, we know that we can set up the ALU operation with function 3 and 7. We want to load the ALU output register, and we need to select the source registers, A and B, or RS1 and RS2. We also have a small optimization here. If the destination register is X0, then that is effectively a no-op, and we will then skip the write-back section. If it isn't X0, then we do the write-back. And in this case, we set up the write signal, we select our source, and at the same time, we also set up for reading from memory when we transition back to the fetch stage. This is the RType. So with this in mind, we can now go to the HDL code and code up both the execute and the decode states to figure out what we need to do. Here we are in the control matrix, the HDL code, and we'll begin looking at the decode section first. As you can tell, we already have our load set up from the last episode. So let's pop open our section here that does the routing to the execute stage. And we know that for an RType, the next execution or instruction register state is RType. And that'll set us up for the next section, which is the execute. So we come down here and we look at that R state, and we know that the R state has been set to the RType. So it'll hit this section right here. And according to our FSM and the data flow diagram, we know that we need to load our ALU register output, set our two sources, A and B, determine the ALU operation, which is a concatenation of function 3 and function 7, and then look to see if there is the destination register is 0 in this case. If it is, we go straight back to the fetch state. This is the equivalent of the no-op instruction. Otherwise, we go to the write back section or next state. Pop that open and you can see that we're setting the WD source to the ALU out, and we're setting the register for writing and finally we set the memory read for the next state, which is the fetch state. In that case, we need to read out the instruction on the falling edge of the clock, and then when we arrive at the fetch, we have the instruction ready to go. So that's the HDL code. It's just adding in these two states and then updating the decode state to pick that control flow instruction state. And that's it for the RType instruction. Now we're ready to write some machine code in order to test out these types of instructions. Here we are inside of our assembly files, which I put inside of markdowns, and our focus is on the add instruction. And in this case, we're adding two operands, x1 and x2, and storing it into x3. To focus on the add instruction, we'll preload x1 and x2. We can do that via the register file. We just go in and set bank 1, which is x1 to 5, and then x2 to 6, and we're good. Now to build the add instruction, we need to break it down into its bits and into its columns. We know that the opcode for arithmetic is this. Our destination is going to be 3, and then function 3 and 7 specify the specific type of operation we're going to do, the arithmetic operation. And then our two operands, 1 and 2. If you break this down into nibbles and then reassemble it into hex, this is the value you'll get. And we place it at address 4 and our e-break at address 8. And when we place the instruction at 4, remember, because our reset vector is pointing to there, to the very first instruction that we need to execute. And so now we're ready to run the simulation, and we expect x3 to have the value b in it, because 5 plus 6 is 11, which is b in hex. So here we are at the timing diagram, and as you can see over here to the left, we have the reset sequence. This is what our processor does every time it comes up. We've covered that. The only difference is that our two x1 and x2 registers have been preloaded with 5 and 6, our two operands that we're going to operate on. And then x3 will be the output. Currently the initialize statement for that also has an 8 in it, so it has some value 8 that we placed in there. Next up would be the fetch sequence for the instruction itself, and that's where it is determined that it's an RType, and there is our instruction. So far things are looking good. Another thing to look at is the program counter. We started at our reset vector, we found our first instruction, then we auto-incremented to the next instruction, and then auto-incremented just before the break. So that's all going according to plan. We can see our usual 2 reset program counter loads here, and here is where we're loading the program counter with the address of our instruction here, 8. That would be the reset vector once we get there. Let's look at the registry file during the RType instruction. We can see here that as it's moving along through the instruction, we're doing our arithmetic, and eventually we're going to reach the write back stage, and that's where we bring the write signal down low, and we take whatever was in the output of our register down here, which is B, so it's set up for the load, and we write it into x3. And that's exactly what's happening. We know that also during the instruction itself, we're going to add the two operands together, and there they are, 5 and 6, and we know that that's what it is because the instruction itself had what it was. The register's instruction itself had the address of both registers, and the outputs show up on the input of the ALU. That's what we expect. We get the sum, which is B, and eventually it's loaded in. So the RType instruction does look like that it's operating as expected. We can ignore the MMU for the most part, except for right up here where we're doing one more read from memory, and that's during the fetch stage because that's what we're reaching into here, and we pull out the e-break instruction, which is what we eventually determine what it is, and we execute it, which of course immediately halts the processor right here. So things are going according to what we expect. The RType instruction is doing exactly what we expect it to be doing. As an extra bonus, let's go ahead and test out our short circuit if the destination register is X0. So I set the destination register to 0, recalculate the instruction, the machine code, breaking it up into nibbles and then reassembling it into hex, and then I've copied this value right here into the RAM location and placed it here. Now let's go ahead and run the simulation and see if it removes one cycle out of the simulation. So here is the simulation, and sure enough, our circuit, our flow, has been interrupted and shortened by one cycle. You can see that the RT complete is no longer present and that the cycle count is much shorter. So the short circuit is actually working. We've added these two instructions, but the X3 register still has the value 8 all the way through. We've done nothing. This is equivalent to a no-op instruction. We've arbitrarily added two values together, but we didn't store it anywhere. And that's what we expected, so yay! Excellent, we completed our very first operational instruction type, and this covers 10 instructions all at once. We have arithmetic, Boolean, shifting, and setting of flags, or bits in this case. In the next episode, we'll cover immediate form of these very instructions, all of which are of the iType category. The load, the jump and link register, eCall, and eBreak, which we've already implemented as a very simple black hole. So, until next time, peace.